Welcome to the third lecture of Deep Learning at the University of Tübingen. In this lecture, we're going to introduce deep neural networks. The lecture is structured into 4 units. In the first unit, we're going to continue our discussion on backpropagation, this time with arrays and tensors. Then we are going to talk about the famous XOR problem, which led to this decline of deep learning research in the 70s. And then we are going to introduce our first deep neural network, multi-layer perceptron. And finally, we're going to discuss some properties of these multi-layer perceptrons in terms of what they can represent, what function classes they can represent. So let's get started with backpropagation with tensors. So here's a little recap, as this unit directly builds upon unit 2.3, where we have started our discussion on the backpropagation algorithm. And this is just a recap of one of these computation graphs and how backpropagation works in these computation graphs. So here, in this case, we're considering a loss function that depends on x via our functions u and v and y, and which we can write in terms of this program here on the left: y of x, u of y, v of y, and l of u and v. Or if we write it in terms of a computation graph, we have this computation graph here on the right. Now, the goal of the backpropagation algorithm is to calculate gradients of the loss function with respect to any variable in the computation graph. And for that, we need to first compute the values of each variable using the assignment sequence, the program, in the so-called forward path. So we go along the direction of these black arrows, and then we go backwards, propagating the gradients backwards to all the individual nodes in the graph. And this is called the backward pass. We start with the gradient of the loss function with respect to itself, which is 1, and by applying the chain rule of this current or global gradient here, times the local gradient of L with respect to u, and obviously we obtain the gradient of L with respect to u, which we store at this node in the graph. We also go backward this edge and obtain the gradient of the loss function with respect to v, which we store at the node v. And then we continue to go backwards by applying the chain rule. For instance, we calculate the gradient of L with respect to u, which we have stored here, times the local gradient of u with respect to y. This is this edge here. And we calculate the gradient of L with respect to v, which we just need to read off because we have stored it here, times the gradient of v with respect to y. And since we have this head-to-head relationship here at this node y, since there's 2 arrows that are joining at node I, we need to exploit the multivariate chain rule here and add up all the incoming gradients. This is indicated here. And then we continue and, using again the chain rule, propagate the gradient further and calculate the gradient at this node here, the gradient of the loss function with respect to this variable. Now we have calculated all the gradients of the loss function with respect to any of the nodes in this graph. How can we implement this? Well, each node in the graph, we consider each node in the graph as an object in the sense of object-oriented programming. This is what we're doing in the educational framework. And each of these nodes has, or each of these variables has a attribute, a value attribute and a gradient attribute. The values are computed in the forward pass, so we simply follow this assignment sequence and implement it in our programming language as such. And then we start the backward pass by setting all the gradients to 0. So xgrad is the gradient of the loss function with respect to the variable L. Ygrad is the gradient of the loss function with respect to y, etc. And then we set the gradient of the loss function with respect to itself to 1. This is where we start, the head of the graph, the final node of the graph. And then we backpropagate this gradient by applying the chain rule. So we compute the gradient of the loss function with respect to u as the gradient of the loss function with respect to itself, which is 1 times the local gradient of the loss function with respect to u. And we need the values that we have computed in the forward pass here, because we need to evaluate the gradient at the location of these variables, or at these variables. So we do this for u, we do this for v, to compute the gradient of the loss function with respect to d. And then here you can see that we have been using here this plus equal notation in order to be able to sum up multiple gradients, which is important because we need to do this at these points where we have two heads in the backward pass pointing towards the same node. So here we have this situation where we add to the attribute gradient of the node y twice, because we have this head-to-head relation here, right? And then we continue to x. Okay, so far so good. Now, what we have considered so far is computations on scalars. So we have considered functions like this one here, where we have a scalar. Typically when I, in the notation I'm using here on my slides, I use non-bold symbols, non-bold small symbols for scalars, and bold symbols are reserved for vectors or matrices. Matrices are typically capital variables, and vectors are bold non-capital variables. So in this case, these are all scalars. We have this affine transformation. We have a 1D to 1D sigmoid mapping that outputs a 1D value. So these are all scalars, input and output. Now, what we want to consider now, which will make our life much simpler when we go on to consider deep neural networks, or our first instance thereof, multi-layer perceptrons, is to be able to express computation graphs not only in terms of scalar variables, but in terms of higher order variables such as vectors or matrices or tensors. So here we have an example where we have a affine or linear transformation in terms of a vector. So the input is now a vector x that is multiplied with a matrix A, and where we add another bias term b. This is a vector as well. And then we apply the sigmoid function. The sigmoid function here is still a 1D to 1D mapping, which is applied element-wise. This is a little bit implicit in this notation, but this is what this notation means. If I use the sigmoid of a vector, then I mean I apply this element-wise to the vector. And then of course the output is a vector y as well. So again, as in the scalar case, the matrix A and the vector B are objects with attributes value and grad, where in the forward pass we want to compute the values, and in the backward pass we want to compute the gradient of the loss function with respect to these matrices and vectors. So for instance, A grad stores the gradient of the loss function with respect to A, and B grad stores the gradient of the loss function with respect to the vector B. Now, if we were to compute a gradient of a vector with respect to another vector, we would obtain a matrix, which is called the Jacobian matrix. However, in deep learning, we are almost always dealing with the special case where the output node of the computation graph, the loss node, is a scalar value, returns a scalar value. Even if we would have multiple loss functions, we would typically combine them linearly with some weights in between, and the overall loss function with respect to the variables would still be a scalar loss function, right? Because we want to optimize it, and we want to optimize a single value. This means that the gradient of the loss function with respect to any variable in the computation graph doesn't change the dimensions of that variable. So the gradient of the variable, of the loss function with respect to the variable, has the same shape or dimension as the variable itself. For instance, a grad, which is the gradient of the loss function with respect to the matrix A, has the same shape or dimension as the matrix itself. So if the matrix is a, let's say, 3x3 matrix, then a grad is also a 3x3 matrix. It has the same dimension, has the same number of values. Okay, so now how can we go about it? How can we actually now run the backpropagation algorithm, not on scalars, but on these vectors or matrices? The key insight here is that any matrix vector computation, like the one that we've seen before, can be written as loops over scalar operations. Here I've used the substitute variable u, which is a vector, to substitute ax, so that we can in a first step calculate u, and then in a second step calculate y. If I were to express this equation here using scalar operations, I can do so using loops over these scalar operations. And this is illustrated here in the bottom. So we start by setting all the values of the variable u, of the vector u, to 0. So we have a loop that loops over all the entries of u and sets it to 0. And then we have another loop. This is a loop over two indices, I and j, where we now implement this matrix vector operation here as this loop over I and j. What we do here is we add to u at index I the value of a at location ij times the value of x at location j. This is exactly implementing a matrix vector product. Right, if you look at it, you see that we have multiplied each element of j to this matrix A at the correct j. And we do this for each index I, for each row element I. So I is the row and j is the column of this matrix X. This is a straightforward loop definition using loops of a matrix vector operation. This is how it would be implemented on a computer. And then for calculating the value of y, we can again have a loop over all elements of I. Now, this is completely independent of each other. We don't have to consider any other variable inside because we have just like a element-wise application of the sigmoid, and the addition is of course also element-wise. So we can do this completely independent of each other, and we simply apply the sigmoid of u plus b at location I or index I respectively. As you can see, all of these equations that you see here are purely scalar operations. Because here we have indexed into matrix A, we have indexed into a scalar element of index A at location I and j. Now this is great, because now, since we have reduced it to the scalar operations, we can basically reuse the same ideas, the same derivations that we made before, and define the backpropagation algorithm exactly the same way, because we have effectively just a more complex set of scalar operations, but it's still scalar operations. We've broken it down into loops over scalar operations. So let's look at the backpropagation of this particular equation. So for the backpropagation, we start here with the last line, and then we can go back to this line. Starting with the last line, this is just a repetition from the slide before of this last line. This is the forward pass. Now if we want to compute the gradient of the loss function with respect to u and with respect to b, we simply apply the chain rule. And because this is completely, each row or each index I here is treated completely independently, this is really trivial. It's exactly the same thing that happens here as before. We're again using this add notation because we assume that there might be other variables in the computation graph that might also add gradients into this node. So we're always going to use this plus equal notation here. But what happens here is very simple. It's simply, this equation is simply saying the gradient of the loss function with respect to u at location I is the gradient of the loss function with respect to y times the gradient of y with respect to u. And the gradient of y with respect to u is the derivative of the sigmoid times the inner derivative, which is 1, because we have just a linear expression here. So this u, the derivative of u with respect to u is 1. Right, so again, we have this backpropagated gradients and the local gradients. Right, and it's again just the application of the standard chain rule. And the same for the gradient of the loss function with respect to b is again just the gradient of the loss function with respect to y times y with respect to b in this case. And again, b appears only linearly here, so the gradient of b with respect to b is 1. It doesn't appear. Okay, so let's go back now one step to this second equation from the forward pass, which is this one here. Right. Now we have already computed the gradient of the loss function with respect to u and b. What we want to compute now is the gradient of the loss function with respect to a and x. Now here it becomes a little bit more tricky because we have a more complex relationship. Here in this case we have a loop over I and j, and the value of u at I is a sum over multiple terms. So we need to sum over multiple j's here, right? Because this is a matrix vector multiplication. There's multiple a's and multiple x's that play a role when we want to calculate the element I of variable u. However, this equation here itself is a scalar equation, and we can utilize again the same chain rule as we've used before. For instance, the gradient of j with respect to a at location I and j is simply the gradient of the loss function with respect to u at location I times the gradient of u with respect to a at location I and j. And you can already see that the value or the variable I, a, j appears only once here, which means that from this sum of multiple terms here, we only draw in the value of x at location j, because only at that location we have this variable a, I, j appear. And this is why we draw in this element here. And then of course we do this for all the elements of the matrix A, or of the gradient matrix. And then we do the same thing for the gradients of j with respect to x. So what we've effectively done now is we have reduced the seemingly more complex backpropagation algorithm for vectors and matrices back to the scalar case by considering loops over scalar operations. And that's a very simple way of looking at the backpropagation algorithm and also of implementing the backpropagation algorithm, because it's quite obvious to understand. In practice, all deep learning operations can be written using loops over scalar assignments. And this also works for higher order tensors. It doesn't stop at matrices. Often in deep learning, we have fourth order or fifth order tensors. A tensor is a higher order generalization of a matrix. A matrix is a 2D structure, and a higher order tensor could be 3D or 4D. In this case here we have a 3D tensors. And we have a loop here over 4 indices because we have this multiplicative contraction here of this tensor, this 3-dimensional tensor A and B. But again, we can express the forward and the backward paths using these scalar operations, which allows us to very easily write them down. Okay. So another aspect of deep learning where this higher order tensors, operations on matrices and vectors is relevant is when we consider mini-batching. So what is mini-batching? Let's first motivate why we need it. Source code, or the programs or the sequence of assignments that we always considered in the previous slides and in Unit 2.3, has 2 components. There is a slow part to it, which is the sequential application of operations as we would code them in Python. But there's also a fast part in it, which is these vector and matrix operations that can be very efficiently executed in NumPy, for instance, using these BLAS single instruction multi-data instructions. So even on the CPU, you get some benefit of parallelism using these special SIMD operations. These are highly optimized operations that we can just call with NumPy, right? It would be much less, orders of magnitude less efficient if you would write a vector matrix operation in Python as a for loop compared to running this on this highly optimized binary BLAS code. And similarly, if we were implementing deep neural networks on GPUs, which is common practice today, and this is actually the reason why they are so popular, because we have now a tool for very efficiently training them. We can utilize tools like CUDA, where we can run these operations, which are often highly parallelizable, completely in parallel on a lot of kernels of these GPU cards, where we can have maybe 4,000, 5,000 parallel processing units that completely in parallel execute these operations for us. So there's this slow part where we have sequential ordering in the way we execute the operations. And then we have this fast part, which is this vector matrix operations that appear, for instance, in this affine term that is the argument of a sigmoid. Now, our goal should, of course, be that the fast part dominates the computation in terms of the wall clock time. We want to push as much of the computation that we do overall into the fast part of the code, into these vector matrix operations. In other words, we want to reduce the number of slow sequential operations, for instance, Python loops or the operations in a computational graph, by running fast vector matrix operations. And we can do this, for instance, in the sense of doing gradient descent, we can do this by running or obtaining gradients over multiple data points at the same time. We can at the same time input multiple data points into a computation graph, pass them through the computation graph forward, and then in parallel also compute the backward pass to obtain the gradients of the loss function with respect to the parameters of all the data points in parallel. And that's called mini batching. And that's really essential for making deep learning efficient and fast and useful. And it's also used in stochastic gradient descent that we're going to talk about in the next units. So here is an example of the affine and sigmoid transformation applied to n data points simultaneously. So in this case here, I've written XA instead of AX, because what I did here is I've used the standard notation of stacking each data vector X into one row of the matrix X. So matrix X is a matrix with n rows, which are the data points, one row per data point, and d columns, which is the dimension of the data points. Let's say we have 32 input dimensions and 100 examples. So we have a 100 row, 32 column matrix X. Each row in X is a data point. And then we multiply this with matrix A. This is the linear part, the multiplicative part of the linear transformation. And then we have our bias vector, which is a m-dimensional vector, which is broadcast into a matrix B with n rows and m columns. Broadcasting is a very standard operation in Python, if you're familiar with Python or NumPy, which is basically, in this simple case here, just copying the vector B into all the rows of the matrix B. So all the rows of the matrix B have the same elements, which is the vector B. Yeah, and then, so this equation here then does the linear transformation of all data points simultaneously because of the way we have written it and the broadcasting of B into matrix B. And then we apply, again, element-wise, in this case not to a vector, but to all elements of the resulting n by m matrix, the sigmoid transformation, to obtain a n by m matrix Y, which is the output of this affine plus sigmoid transformation. If we write this down in terms of source code, we now have loops. Right? Here's again the point of loops and loops over scalar operations. Now we have loops also over the batch index B. Right? So this is the index of the element within the batch. And you can see that the variable u depends on this, and the variable x and the variable y. So the input and the output and all the intermediate calculated variables depend on this additional batch index B, which is the index of the data. The parameters, in contrast, they do not depend on this additional batch index because it's an index of the data. It's not an index of the parameters. The parameters are the same. So A and B do not depend on this index. Instead, if we do a gradient update now, we do this gradient update for all the batch elements onto the same gradient elements of the parameters that we're interested in, A and B, for instance. Also, and we'll see this in the next slides, by convention, the gradients are averaged over the batch. This is a little bit of an unfortunate convention because it doesn't directly correspond to the maximum likelihood principle that we've seen in the previous lecture, where we wouldn't have this averaging, but it's just a convention that we average over the batch when we calculate the gradients. So how can we now efficiently implement this? Let's consider only the affine transformation, which is the inner part of this expression here. So this is the affine transformation, again applied to n data points simultaneously, where we have this input matrix X with the rows storing the data points, or the inputs if it's an intermediate layer in some deeper network, could be the output of the previous layer. And then we have this bias B broadcast into matrix B, and the result is Y. So how would we implement this very concretely now in the educational framework? Well, the forward pass is just a standard NumPy expression of a matrix vector multiplication and an addition. And these are all very efficient NumPy operations, as I mentioned before. So this is something that is very efficient and fast. So that's why it's important to pass as many data points as basically fit into our memory in parallel through these operations, because as soon as I execute these operations, I'm not within Python anymore, but I'm inside these BLAS operations where this entire expression is evaluated very fast. However, it can be tricky to define these loop over scalar operations. In this case, for the forward pass, it was easy, but it can be tricky to define this for more advanced backward operation. So in this case here is still simple. If we have the gradient of the loss function with respect to x, then this is simply multiplying the gradient of the loss function with respect to y times the gradient of y with respect to x, which is A transpose. If you would translate the loop over scalar operations that we have derived on the previous slides, you would see that this corresponds exactly to this expression of the matrix multiplication of this matrix with respect times the transpose of A. Right. And then for B, we have the gradient. We have just the gradient of the loss function with respect to y, because the gradient of y with respect to b is 1. However, the gradient of the loss function with respect to a is a little bit more challenging. Again, in this loop over scalar notation, it's kind of obvious. It's very easy to see. However, to translate this, because we don't want to use here, of course, loops in plain Python, in order to translate this into efficient NumPy primitives can be hard. In this case, this corresponds to this strange expression here on the bottom, where we have this new axis generation and a product of a tensor that corresponds to this relatively simple loop over scalars, and you need to be almost a little bit a NumPy wizard to actually come up with these expressions, and that's also why the complicated expressions we will provide for you in the educational framework, so that you don't need to implement them yourself. So in summary, computation graphs are easy to understand using the loop notation, and we really just have loops over scalar operations. That's why we're just applying the scalar chain rule, and in this case as well. However, implementing it efficiently using NumPy primitives is not always obvious and requires some expertise.